There's a further talk on anomalous resistivity by Feder and Orens. I think the talk is going to be given by Dr. Feder. It's entitled The Effects of Anomalous Resistance on Auroral Birkeland Currents. Today I'm going to talk about something a little different than what's written up in the abstract. The reason being not that what was written up in the abstract is untrue, but I think I have some more interesting results which have been developed very recently that I would like to show you. In particular, we have just within the past couple of weeks seen some three-dimensional models of auroral arcs, and we can actually see the two-dimensional distribution of Birkeland currents in the horizontal plane, and also the electric fields around the arcs in the horizontal plane. Before I begin to show you some of the results, though, I'd like to acknowledge the help of Dave Book with a flux-corrected transport algorithm, which is essential to do this sort of solution. The first slide will show you a arc-like, let's see where we got a button someplace. Yeah, there we go. And what we start out with in an arc-like structure. The axis down here is the x-axis. It points southward in this particular model. This is the y-axis, points eastward in this particular model. We have assumed that the magnetispheric electric field is 25 millivolts per meter in the southward direction and is a negative 5 millivolts per meter in the eastward direction. That is, it's a westward field. The dimensions here are 98 kilometers across the grid this way, 980 kilometers across the grid this way. So you can see that this arc structure here, right in the center, is rather elongated. In fact, it's roughly 1, 2, 3, maybe 400 kilometers long, while it's maybe slightly more than 10 kilometers wide. What you're seeing here are contours of the particle Birkeland current, that is the electron flow. This is different than conventional current. The contours here between 1 and 4 are current or are electrons flowing into the ionosphere. The contours between 5 and 8 are electrons flowing out of the ionosphere. So here the conventional current is out, the precipitating particles are coming in. Here the current is in. This is what the currents look like at time 0 when we start up our arc. As yet there's no density enhancement from the arc, and the inflow is caused by the precipitating current that we assume. The outflow is caused by a polarization that takes place almost immediately. The next slide will show what the pattern looks like in the central plane of the arc. This is an XZ plane, which is center of the arc, and in the y direction. So that what you essentially see here are these small currents flowing out on either side, or the electron flow out on either side, but the rather large precipitation current flowing in here. The numbers here are, down here is 6 times 10 to the 9th electrons per square centimeter per second. I should probably mention also that these are the electron currents which exist at 200 kilometers just above the conducting region of the ionosphere, at least the horizontal conducting region of the ionosphere. This particular slide here shows what the currents look like in a east-west plane, vertical plane, or amplitude. And again, we see that the arc is about 400 kilometers long. We see essentially the precipitation coming into the arc. The next slide here is the steady state condition for the Birkeland currents. It's considerably different than what we started out with. In particular, what we can see is we can see the electrons coming into the arc here in the precipitation region. Almost all of the downward flow of electrons are the precipitating electrons. There is very little induced downward flow of cold electrons in this particular model. Over here, in these contours, we see the upward flow of cold electrons which conserve current in the ionosphere. We see, first of all, the result, the currents this way, the in on this side, the outflow of electrons on the other side conserves the cross arc current carried by ions in the ionosphere. The distortion in this direction of the profiles is to close the electrojet currents which are flowing along the base of the arc in the westward direction. This again is a picture of the Birkeland currents across the arc on the center line, and this is the southward axis, and we see here that the currents are flowing out to the northward side of the arc, or at least the electrons are flowing out to the north of the arc, and we see that most of the currents that are flowing into the arc on the southward side are actually being carried by the precipitating electrons. This looks very much like the first slide I showed you of the precipitating electrons. Along the center line of the arc now, in the east-west direction, we see here, of course, a few electrons flowing out at the eastward end of the arc due to the westward electrojet. But on the center line, essentially, for the most part, we see just the precipitating electrons coming into the ionosphere. The next few slides, I'll show you what the electric field pattern looks like. This will take some explanation. There's a lot of numbers here. I hope you can see them. I'll try and trace them out a little bit. This is the x-directed electric field in a north-south plane, or in a series of north-south planes. What are shown here are 5 separate planes. They are separated by 100 kilometers each from the center line of the arc in both the east and the west direction. The center line electric field here starts out at 25 millivolts per meter, rises up to something like 35 millivolts per meter, falls down to about 12 millivolts per meter, and returns back to the ambient 25 millivolts per meter across the arc. We see that the arc is polarized in the north-south direction over a considerable portion of its length, because the next 2 planes here, separated by 200 kilometers and 100 kilometers on either side of the center line, again rise up to a fairly high electric field, then fall down to fairly low values, and again follow essentially the same pattern. We can see also that the scale size of these electric field variations are on the order of maybe 10 to 20 kilometers. This is again the southward electric field, but now we're looking at planes which are along the arc in the east-west direction, the long axis. And here we can see the enhanced field, which occurs to the northward of the arc. Down here are the reduced fields, which occur in the center of the arc. This slide shows the polarization that you get on the arc end to end in the east-west directed electric field. The level here is 5 millivolts per meter westward. And we see that the arc is polarized such that there is an increase in the westward directed electric field to the east of the arc, a reduction of the westward directed electric field in the arc, and to the west of the arc. In fact, this particular sort of data here looks a great deal like some measurements that Moser reported a few years ago with balloons when he saw X-ray events come overhead. And what he essentially saw is an increased westward electric field as the X-ray events approached him, a reduced westward electric field when the arcs were overhead. And this is essentially what this sort of pattern shows. And finally, this shows the extent of this polarization field in the westward direction along the x-axis, and we can see that the extent of it here is about 30 kilometers wide in the north-south direction, so that indeed it could possibly have been measured by Moser's balloon, considering that the polarization was very long in the y direction, and it indeed covered a rather large region of the ionosphere. That's the last results I have to show on 3D arc models. I would like to make one comment in general about the electric fields that one might expect from arc models like this in the ionosphere. And it's that in all the arc models I've looked at, both 2D models and 3D models, I find that the polarization field parallel to the field lines is such that the electric field is pointed downward on the field lines. This will not accelerate electrons downward, it accelerates electrons upward. An arc, because of the precipitating electrons coming in, carrying most of the upward conventional current, downward particle current, is essentially a negative charge region. And it's a hole in the potential. And it's very difficult by any dissipative mechanism, whether it be anomalous resistivity or double layers or anything else, to accelerate any energetic particles into the ionosphere. They would all go the other way, at least from these studies it was indicated that they would. Thank you very much. Yes.
Did you allow the electron density to be increased in the arc due to the precipitating electrons?
Oh yes, the electron density in these, I should have mentioned it, the electron density in the E region in these particular arcs is enhanced about 5 times over what it is outside the arc. The other thing I might mention is that in these particular arcs, the Hall to Pedersen conductivity ratio inside the arc was about 1.4 to 1.6.
I'm sorry, I don't quite understand what some of your assumptions were in this. You assumed a certain precipitation, did you, as an
Right,
starting
okay.
point?
We solve a continuity equation for the ions in the ionosphere. We assume the production function that goes into that. We also solve an equation which requires current conservation in the ionosphere, which of course requires the flow of Birkeland currents between the ionosphere and the magnetosphere. Finally, we assume that there is a resistivity to the flow of the Birkeland currents along the field lines, that this resistivity resists the currents and causes the arc to polarize. And what I'm showing you here is the fashion in which the arc polarizes and where those currents flow.
You assumed the parallel resistivity was a constant or something like this, did you?
For this particular model, it was assumed to be a constant everywhere. What I was originally going to talk about was you can assume clearly any sort of pattern you want, in fact, further resistivity. And in the two-dimensional models, assuming different sorts of resistivity patterns around the arc actually led to different Birkeland current distributions, so that measuring Birkeland currents in electric fields could tell you something about the resistive mechanism that might be operative. I have not seen enough three-dimensional models to know if this sort of behavior is still true, but I would expect it is, since everything else that I learned about two-dimensional models is carried right over into the three-dimensional arcs.
I don't know whether I correctly understood your very last statement. If I did, I'm puzzled by it now. The downward electric field would, in other words, then retard precipitating electrons. Now that precipitating electrons come from much higher up, we know from measurements of Heikela and others. And furthermore, there are calculations by Rees, Stolarski, and people who have compared either in one calculating forward or backward the observed 3914 emissions with these fluxes. Mm-hmm. There's general agreement. Now, if there's a retarding field, that would mean that these particles, when they hit the area of the emission, like 120 or so kilometers, they would have much lower energies than they would if there were no retarding fields. So.
Okay. No, I'm not saying that there's a retarding field in the region where the currents are coming in. Essentially, the retarding field is what's driving the electrons upward to return the precipitating particles. What I am saying, though, that it does not seem that it's possible to apply a dissipative mechanism to the precipitating particles to get downward electric fields, and therefore to use either ionospheric feedback, use some nonlinear ionospheric feedback to create arcs. That doesn't seem to be possible, because you can't dissipate the flow of energetic particles to accelerate energetic particles, essentially. And
okay, but then how, I mean, since you have these downward fields, which would decelerate the precipitating particles, that would critically affect the spectra that are observed.
no. The downward field is in a different place than the precipitating particles are coming in.
Oh,
You know, it's over on the other side of the arc where the currents are actually flowing upwards. The other thing is, I don't mean to say that there are not electric fields, parallel electric fields around arcs that are directed upwards. But what I am saying is that a dissipative mechanism that involves interaction between the ionosphere and the magnetosphere probably cannot lead to these. We have to look for the source of these fields elsewhere, and presumably it's way out in the magnetosphere.
You said you introduced anomalous resistivity on the field line in order to get the arc to polarize. Could you just elaborate on that a bit?
Well, if you want an auroral arc to polarize, you have to assume something about the sorts of currents that can flow. And if you make, well, you can make a number of assumptions. You can make assumptions that virtually no current flows, or you can make an assumption that the current flows freely. Well, if you make the assumption that it flows freely, the arc doesn't polarize very much. And essentially what you have to do is you have to make the integrated resistance along the field line between the source of the electric field, the magnetosphere, and the ionosphere be about equal to the integrated resistance across the arc in the ionosphere before one gets very much polarization.
With regard to your frame of reference, as I remember some time ago you were thinking of neutral winds blowing through the arcs, and I wondered what effects, say, a 200 meter per second neutral wind would have, say, north-south. Have you looked at that yet?
Yeah, not in three-dimensional models. In the two-dimensional models, in fact, we have, and it does change the polarization, but I don't have any examples to show today. But it behaves very much like a parallel electric field to the arc, where one assumes that the source of particles in the magnetosphere does not convect in that field. In other words, remains in one place.
I mean, there's certainly a great variety of observations around arcs and different auroral forms, but I'd say certainly the most general observation is that there are not signs of strong electric fields bordering auroral forms. In other words, next to auroral form just sort of represents a dip in the electric field rather than something with enhanced wings on it. And I was also wondering, in other words, the evidence, I would say, is that the currents flow rather freely along field lines. And did I get it right that you were closing the Hall current component by means of a Birkeland current, or was the Hall current, I don't see how the Hall current flowed at all with the polarization you were putting in.
The Hall current did close with the Birkeland currents. And in fact, that's why the second slide I showed of the Birkeland currents, the inward current was in fact considerably to the west of most of the outward current.
I'm really not sure what it means when one closes a Hall current with a Birkeland current. I just lose sight of what that means.
I'm not sure exactly what it means either, but clearly it has to close someplace.
Well, my point is that I think the evidence is that currents flow very freely along field lines, and there's nothing wrong with closing Hall currents along field lines.
Okay. Well, I can say one other thing, though, about flowing freely along field lines. This may be, but one of the alternative models to the structure of electric fields in arcs requires that the magnetospheric generator be a resistive generator, whatever that means, so that one can somehow, in some fashion, load it. The particular form of my equations describes that equally well, and you can't get away from the fact that if there is some potential across the magnetospheric generator, and one puts a load on the thing locally where the convection cannot flow through, that fields are reduced, somewhere outside that region, the flow is going to be faster. And in fact, this is just what the arcs are essentially showing, that if one placed this resistor in the magnetosphere and made it a generator that you could load, what's happening is that the magnetosphere is attempting to flow around this inhomogeneity, which happens to be an arc in the ionosphere.
The question that goes back to the impedance of the generator, of course.
Yeah, true. But the other thing is that you can't drop the field very much inside the arc unless you have sufficient impedance in the generator.
Well, I was just going to say that the observations of electric field structures near the edge of arc have been made as many times as they haven't. I mean, I think arcs are very complicated, and sometimes the fields are small inside them, and sometimes they're large. We've seen evidence at this conference where the fields were large inside and at boundaries of arcs, and Hepner and other people have seen smaller fields, and Moser has seen smaller fields associated with precipitation patterns. So there's no general statement one can make about the fields, I don't think.